my name is Ronak Patel, and this is my video lab report on constant velocity. The purpose of this lab was to find a real-life example of an object moving at a constant velocity and understand the physics behind how it works through the application of Newton's second law of motion. A baseball was rolled on the floor surface at a constant velocity, and the motion was analyzed using tracker and modeled through VIDLE. The computational model and experimental model were compared to understand that there was no net force acting on the system and there was constant velocity. The two main principles applicable to this lab are Newton's first and second laws of motion. The first law states that an object in a state of uniform motion remains in that state of motion unless an external force is applied to it. Basically, an object moving at constant velocity will continue to move at that constant velocity unless acted on by a net force. The second law is also known as the momentum principle, where the change of momentum of a system is equal to the net force acting on the system times the time interval delta t. And as you can see in the picture here, the change in momentum is equal to the net force times delta t, and once you divide this by the mass, you get the Newton's second law, which is the final velocity equal to the initial velocity plus the net force divided by mass times delta t. And if you want to simplify it even further, divide by the change in t, and you get what many of us know as the net force equal to mass times acceleration. At constant velocity, acceleration equals 0, so by substituting acceleration into the formula, the net force is equal to ma, mass times acceleration. The net force is also equal to 0, implying constant velocity because final velocity is equal to initial velocity. Now this is the video of the baseball moving at constant velocity being analyzed with the tracker. The baseball is the system and everything else is considered the surroundings. After plotting the points of the baseball's motion, the graph on the upper right hand corner appears to be linear, meaning there is constant velocity because the slope of the position versus time graph is the velocity. The right was chosen as the positive x-axis, so the graph slope is negative because the baseball was moving to the left in my situation. The data table is also useful because it gives the time and position. The time goes from 0 to 1.1 seconds, and the position goes from negative 0.002 to negative 0.821 meters. The data from tracker was appropriately implemented into the skeleton code provided in creating a computational model. The mass of the baseball is 0.075 kilograms. The initial position of the baseball was negative 0.002 meters. The initial velocity is a value we have to calculate by dividing the change in position by the change in time, as shown here. We got a value of negative 0.91 meters per second. The change in time is 0.01, and it is small in order to have multiple points, so the results are more accurate. The while loop in the code shown continues to iterate until the video ends, which in this case is 1.1 seconds. In the while loop, the net force is set to 0. The following line of code represents Newton's second law, and the line of code after represents the position equation relating velocity and the progression of time. The while loop will help create a computational model of the baseball's predicted motion. When the code is ran, the following computational model is shown. By comparing it to the graph on tracker, they are roughly similar, showing the accuracy in the data. The graph by tracker is not perfectly linear, as the slight curve may be due to the curved motion of the baseball. By superimposing the two graphs, the observed motion and predicted motion can be compared. The experimental data deviates from the model data, meaning there were some discrepancies, and that the model I created isn't completely ideal in predicting motion, even though it is roughly linear. One limitation is friction, as the baseball was rolled on a carpeted surface and friction slows the baseball down by affecting the net force. The graph shown was made using a spreadsheet. Now let's answer some conceptual questions regarding the lab as a wrap-up. If the axis was changed, the car would be moving along the positive direction rather than the negative. The slope would be going up and to the right instead. However, with a flipped axis, the object would still travel at a constant speed, but just a different direction. And here it would be up and to the right. Next, in response to the question shown on the screen, From observation, it is not possible to say how many pushes and pulls are added together to get a zero net force. The types and number of forces acting on an object cannot be assumed. All we know is that there is a constant velocity, so the net force is equal to zero. Overall, one way to improve this lab would be to make the object move on a smooth surface rather than a rough, uneven surface in order to minimize friction. Thank you, and this concludes Lab 1.